Welcome back to our class, Module 4.2, Formation of the Orbitals, Chemistry 411, Physical Chemistry 2. Remember, in the last module, we talked about linear combination of atomic orbitals. So now we want to look at the formation of these orbitals properly. We're going to look at orbitals, Born-Oppenheimer approximation again, orbital energies, electronic distribution of these orbitals, molecular potential energy curves, the significance of overlap integral, and we'll conclude. Orbitals. So according to the Born interpretation, the probability of the electron in HT is proportional to the square of the wave function. Remember we said phi squared, that if phi is the wave function of the molecular orbital, then phi squared gives us the probability of finding the electron. The probability density for the molecular orbital is given by, look at it, phi squared is equal to n squared phi 1 SA plus phi 1 SB. If we expand this, we're going to have phi 1 SA squared, 2 phi 1 SA, and phi 1 SB. An important feature of this equation becomes apparent if the probability density in the internuclear axis is examined. Internuclear axis, that is, along the nuclear axis of the atoms A and B, for instance, the one we use for the hydrogen. In this region, both orbitals have similar amplitudes. Therefore, the total probability is proportional to the sum phi 1 SA squared and 2 phi 1 SA phi 1 SA. The first two terms gives the probability of the electron between A and B respectively. The third term is an extra contribution to the density called the overlap density, which is related to overlap integral. We'll still see that. It is crucial because it represents the enhancement of probability of finding electron in the internuclear region, while just explaining where this electron can be found, since we are talking about molecular orbitals. And this enhancement can be traced to the constructive interference of the two atomic orbitals, because along the internuclear axis, once you have constructive interference, it means that you're going to have a kind of plus, that is a build-up of the amplitude. But when you have destructive, then it means you're going to have plus minus, that is a destruction or a flattening or neutralization of the amplitude. Remember your wave equations. Again, we're looking at the Born-Oppenheimer approximation. It is useful in that it allows us to decide on the particular internuclear separation, solve the Schrodinger equation. We have said that. We're trying to repeat some of these things here because it's very important so that you will understand. It is therefore possible to choose a separation. We did this in the last, and obtain the molecular potential energy curve, which we are going to show you. Hence, the equilibrium bond length of a molecule can be identified, and this is the lowest point of the curve. We'll see that. So the same thing, we'll solve this Schrodinger equation, get the values for electron density, just like we said. Let's look at some of those diagrams we have. However, at small separation, still the same thing we have said before. We have the nucleus-nucleus interaction. As a result, the total energy rises at short distances, and there is minimum of the potential energy curve. And this minimum is called the dissociation or bond dissociation energy. And we use the variation parameters. Remember I mentioned C1, C2 as variation parameters. So we use these variation parameters to calculate the energy and make sure that it is never less than the true energy. This involves the use of trial wave functions, where C1 and C2 are variation parameters. We don't want to take you through this variation method. We're just giving you the results. Remember our Hamiltonian, phi h, we have equation 6. Remember our Schrodinger equation, the Hamiltonian. And using that, we'll solve and get E plus, which is for bonding, and E minus, which is for anti-bonding. This gives us the energy of the bonding and anti-bonding, where the energy of the bonding is less than the energy of the anti-bonding. And we also calculate the Coulombic integral, Coulomb integral, J, equation 9. Of course, it gives us the Coulombic interaction between the nucleus A and nucleus B and the electron in that orbital. So we can see that still have our electron charge here. So this gives us this 1sa and then this 1sb. Now we also do the K, which is K is what we call the exchange integral. We calculate the exchange integral. This gives us the exchange integral. Then the overlap integral, which is also very important. And using this simple variation treatment, the dissociation energy was calculated as for hydrogen as compared to the exact value of 2.78 and the equilibrium distance of 0.132 nanometers as against the exact value of 0.106 nanometers. We didn't want to take you through this calculation. It's just for you to note the results that we're able to get using the variation parameters. Now, electronic distribution of these orbitals. Phi squared gives the relative probability of finding an electron in elemental volume of change in, we said dt, which is elemental volume of the sigma. Phi square sigma is equal to 1 when normalized. That is, we're talking about normalized. So the electron density increases as the molecular orbital is formed. In other words, the probability of finding an electron between the two nuclei in the molecule is greater than that obtained when the two atoms are brought together. Whereas in the antibonding, phi minus, there is a point of zero electron density. That is, the electron density decreases as the antibonding molecular orbital is formed. This point is called a node or nodal plane. I showed you a line in between the s orbital when we had, 0 plus 0 minus. That is destructive interference or destructive construction, which now gave us, a line in between the two orbitals, giving us anti-bonding. Now let us look at the potential energy curve for this hydrogen molecule. Look at what we're saying. Look at the lowest energy, which gives us the bond dissociation energy. And this gives us the bond length. So you can see when the molecules here, the potential energy drops as the molecule comes together. And then when the attraction dominates, you have a stable bond here. The attraction has dominated here. Here is when the molecules are too close together, that there is a repulsion and the energy drops. Once we get this minimum energy again, it starts increasing, and here atoms are so far apart that they do not interact. And the lowest point in this curve gives us the bond dissociation energy. Of course, we have plotted potential energy against the distance between the two nuclei. Now, by extension, we're having this to show, the bonding potential energy curve and the anti-bonding potential energy curve. So the same thing here, if you look at this one here, is the same thing as this one here, which gives us bonding. But look at the anti-bonding. Of course, we have compared this with the experimental values and calculated values. You can see calculated is a green line, experimental is a red line, which lies almost very close. So bonding, the electron density transfer into internuclear region, lowering of energy. Look at it, it comes down. For antibond, the electronic density undergo a small expansion around nuclei, increasing the energy. Look at it here. The energy here is more than the energy here, and that makes the molecule to a kind of fly apart. That is, cannot come together. That is against bonding. I would say is anti-bonding. In bonding, there is a minimum energy. In fact, that diagram has explained this. Bonding describes the attractive states, while anti-bonding describes the repulsive state. For bonding, the molecule will stay together, but for antibonding, the molecule will fly apart. Now, in terms of parity, the bonding molecular orbital is symmetrical with respect to inversion about the center, whereas the antibonding molecular is asymmetrical. Therefore, the bonding molecular orbital is said to be even. That is even, and we'll call that Jared. G represented by G will still meet the usefulness of this in the electronic configuration. On the other hand, the antibonding molecular orbital is said to be uneven and is represented by U. Note that this description is only true of homogeneous scarce molecules. So we have Jared and unjared molecular orbitals when they are even or when they are odd or uneven, respectively. The significance of the overlap integral. Remember, we mentioned the overlap integral. Now, what this overlap integral does is to help us to know the extent of overlap. Because if there is no overlap, there won't be bonding. That's what this overlap integral is all about. Now, assuming you have two 1s atomic orbital, if there is no overlap between the two atomic orbitals, then overlap integral is 0, and hence there won't be any bond formation. Let us take another example. It is possible to form a bond. Now we're having two atomic orbitals from 2p. If there is overlap at the nodes, remember the nodes where there are no electron density, which is equal to 0 in this case, we cannot form molecular orbital with 2px and 2py. You can imagine. That's what we're saying. Where there is no electron density, then you can't. If we now take two hypothetical cases with overlap integral S1 and S2, the overlap integral is a measure of the strength of the bond. The condition of maximum overlap is that we need two atomic orbitals to overlap as much as possible to obtain a good or strong molecular orbital. When we have sigma and pi bond, then the overlap integral of sigma divided by the overlap integral of pi bond will be greater than 1. Remember that the strength of sigma bond is greater than the strength of pi bond. This means that a sigma bond is much stronger than a pi bond. Because of this, a pi bond will be more reactive than a sigma bond. Okay, we want to look at this overlap. We have seen this before in the last module. Look at S to S overlap, P to P overlap, and S to P overlap. And we're now saying that the strongness of overlapping follows the order. P to P overlap is stronger than S to P overlap, which is stronger than S to S overlap. All right, thank you for listening. We have looked at orbitals and orbital energies, Born-Oppenheimer approximation again to emphasize the electronic distribution of these orbitals, forming their molecular potential energy curves, and the significance of overlap integral. Thank you. I hope you enjoyed this class. See you in the next class.